I mean, the steel industry stands for almost 9% of global CO2 emissions right now, and that needs to change.
Kia ora, I'm Troy, HERA CEO, and welcome to Stirring the Pot. Thanks for connecting. If you're new, here's what you can expect. We're going to be talking the tough stuff, the things that keep us metalheads up at night. There are many challenges facing our industry, and equally many opinions on how we should tackle them. Stirring the Pot provides a facilitated forum to discuss and challenge these viewpoints.
So let's get to the nuts and bolts of it. Today we'll be talking with Thomas Hörnfeldt, who is the Vice President of the Sustainable Business at SSAB, who throughout his career has worked in the metals, construction and process automation industry. Join us as he chats with our Senior Structural Sustainability Engineer, Amir Shah Mohammadi, about SSAB's HYBRIT technology, which has resulted in the world's first fossil-free steel production.
As many of you know, the steel manufacturing industry is a significant contributor to global warming due to its heavy reliance on fossil fuels. However, there is an encouraging global shift towards hydrogen-based steel production as a promising alternative to the current coal-based method. This shift holds a significant potential for reducing steel industry's CO2 emissions and mitigating its environmental impact on climate change. In this context, I would like to highlight the remarkable efforts of the Swedish steel corporation known as SSAB in leading the way towards fossil-free steel manufacturing. This is happening through their groundbreaking initiative called HYBRIT. HYBRIT stands for Hydrogen Breakthrough Iron Making Technology. This amazing technology has marked a revolution in the steel manufacturing industry indeed. SSAB has achieved this by collaborating with two other Swedish partners, which are 𝗀𝗂𝘀𝗶 Mining Company and 𝗬𝗏𝗏 Power Company. Kia ora, hello everyone. I'm Amir Shah Mohammadi, Senior Engineer and Researcher at Heavy Engineering Research Organization in New Zealand, and today we are honored to have Mr. Thomas Hörnfeldt, the Vice President of Sustainable Business at SSAB. Thomas brings with him a wealth of knowledge and experience in sustainability, business strategy, sales, and marketing. A warm welcome to you, Thomas, and greetings from Aotearoa, New Zealand. If there is anything you would like to add to my intro words, please, this is your space now.
No, that's fine. I just afraid that I will be a bit of an anticlimax after that introduction.
I'm confident you will exceed that, Thomas. So shall we move on to the questions then?
Absolutely.
Okay, Thomas, could you please tell us more about the HYBRIT fossil-free steel project and its current stage of development?
Absolutely. So HYBRIT was first announced as an initiative, as an idea, something that we were going to do in April 2016, at which time we had this idea of abandoning blast furnaces in steel production and move towards what we call direct reduction using hydrogen in the future. An idea that was known, that has been done on laboratory scale, but never in an industrial scale. So we started with a feasibility study, and almost 2 years later, in the beginning of 2018, we announced that everything that we found during this feasibility study made us even more convinced that this is the right way to go. And we also said we're going to build a pilot plant, a small but industrial plant, to learn how to run this process in an industrial environment. That work started, certainly, but even before we had finalized and had the experience of the pilot plant, we were so convinced that this was the right way to go. So we actually already 2019 at the UN Climate Summit in New York announced that we're also going to build a commercial demonstration plant with a capacity of more than 1 million tons of iron to go into production in 2026, at which time we will also launch these fossil-free steels as a commercial product on a commercial scale. So the principle behind this is that in a blast furnace, iron ore, which is pretty much iron oxide, is converted into iron, which means that you need to remove the oxygen from the iron ore. And in a blast furnace, that is done with carbon in the form of coke, and then the oxygen moves to carbon and forms CO2, and you're left with the iron, which is what you want. But also for every ton of iron that you make with this technology, you get at least 1.5 tons of CO2. That's a chemical fact. You can't really do much about it. So what we are now doing instead is that we're exposing the iron ore to hydrogen, and then the oxygen in the iron ore moves to not to carbon forming CO2, but to hydrogen forming H2O, also known as water, as a byproduct. And furthermore, we can use the fact that we have a virtually CO2-free power grid in Sweden, so that we can use green electricity to make hydrogen out of water with electrolysis, hydrogen that we put into our process, and then we get the water back as a byproduct. And that way, we can make iron without any fossil CO2 emissions whatsoever. Now, the traditional blast furnace gives liquid iron as an end result. It, literally speaking, runs in a trough on the floor in our shops. With direct reduction, you get a relatively boring gray lump of iron called sponge iron, and in order to process that further, you need to melt it down to liquid form. And to do that, we use exactly the same technology that is used for scrap-based steelmaking today. You put it in an electric arc furnace and melt it down to liquid form. But once we have crude steel, all the downstream processes, the alloying, the casting, the heating, the rolling, and so on, they will be the same as today. We just need to make sure that we're using fossil-free electricity and fossil-free fuels in these processes. And it is in the downstream operations that we create the properties that we want to have in the steel. And since these will be identical to today, we can confidently say that our steels will have at least the same performance in the future as they do today, just with the added value of being fossil-free. Question, we have our pilot plant up and running. We're very happy with the results so far. The metallization rate is very good in the sponge iron that we make and so on. And this is a research facility. It only produces a ton of iron per hour when it's operational, and we run it in campaigns and so on. But we'll actually so far produced some 500 tons of sponge iron that we've been able to convert into steel and also deliver to some customers for testing, demos, concepts, and so on. And together with one of our partners, the Volvo Group, we actually also have a limited serial production using these fossil-free steels.
Thanks, Thomas, for your detailed introduction about HYBRIT, including the feasibility study, pilot plans, and the commercial demonstration plan. Also, successful production and collaboration with Volvo Group for limited serial production has been really a notable achievement. Thomas, following this, could you please expand a little bit more on the main infrastructure that steel mills require to implement this technology?
Well, you need to build the so-called reduction shaft where you expose the iron ore to hydrogen. Then you need access to hydrogen, which you can either buy, of course, although the amount of green hydrogen available in the world is very, very small. Most of the hydrogen that is commercially available today is cracked from natural gas, which is not very fossil-free at all. So in our case, we're using fossil-free electricity to make hydrogen ourselves. So that's the other option, that you need to have access to green fossil-free electricity, which I think is the main bottleneck if you look at this globally. And then once you have this, you can make sponge iron. And like I said, in order then to convert that to crude steel, you need an electric arc furnace, which you will have today if you're a scrap-based steel maker. But if you're currently using a blast furnace, then you need to add that as infrastructure as well. So the blast furnace today will be replaced by the hydrogen using reduction shaft plus an electric arc furnace. Once you have that, then the downstream operations would be the same.
Thanks, Thomas, for your informative answer on the infrastructure requirement. Before we proceed to the next question, I would like to return to your earlier statement regarding achieving the same steel properties as we have today. Considering the shift from coal to hydrogen as a reductant, My question is, are there any concerns or potential challenges related to brittleness in the steel when utilizing hydrogen in the reduction process?
No. Sometimes we get questions about hydrogen brittleness since we are using hydrogen. But the hydrogen is not reacting with the iron per se. And if by any chance some hydrogen atoms are hiding in the sponge iron after this process, it will not survive the electric arc furnace and the melting process. So once you have crude steel, the hydrogen is gone.
Thanks for clarifying that, Thomas. With the shift to hydrogen as a reductant, I'm curious if it is possible to produce all current steel types and grades using this innovative approach. Could you shed some light on this matter, please?
We're talking at SSAB a lot about fossil-free steels, but like I just explained, what we're actually changing is the iron-making part of the process. And since we are starting with iron ore, we don't have any contamination or anything. So everything that you can make from a blast furnace, you can certainly make also with direct reduction.
Mm-hmm. Great, thanks. Now let's have an economical question, Thomas. Could you please provide some insights into the cost implications of producing fossil-free steel compared to traditional methods? Actually, we are interested in understanding the potential price perspectives and how the cost of steel production using the hybrid technology compares to the conventional methods.
Well, cost and price are two different things, as we are all painfully aware in business. And we made the calculation when we released the feasibility study in February 2018. And with the European cost level at that point in time, for electricity, for emissions, we have emission trading in Europe, so it costs money to emit CO2. In February 2018, this new technology would have been 25-30% more expensive than conventional steelmaking in a blast furnace. However, we also said already then that this gap will have narrowed considerably when we approach 2026, primarily because the cost of emissions in conventional steelmaking will increase in Europe. And we can see that already today. In 2018, February, the cost of emitting a ton of CO2 in Europe was approximately €5 per ton. Today, it's more like 85 or 95. So we certainly believe that this is going to be a competitive product when we release it to the market. We also know that the demand for green materials in general, including steel, is quite high these days. We see that from our customers already. So we think this will be both a competitive and an environmental advantage for SSAB, and also a competitive advantage for our customers. Like I said, there is a big demand for end products with reduced carbon footprint in the marketplace.
From what you mentioned, it's really promising. Initial 25 to 30% additional cost of hydrogen steelmaking compared to traditional methods will be actually minimized through the implementation of higher carbon taxes. That's really great. And now, Thomas, let's shift our focus to the environmental aspects of the hybrid process. As we have primarily discussed CO2 emissions, mainly in relation to global warming potential, I would like to explore if any potential negative environmental impacts associated with the hybrid process have been already identified. Specifically, my question is, have there been any concern regarding other environmental impact categories like acidification, eutrophication, ozone depletion, or abiotic depletion?
No, not really. We are using water to make hydrogen. But as I mentioned, we will also create the same amount of water afterwards in the process, and we can reuse that water, so that is not really an issue. And generally speaking, I mean, hydrogen is a clean commodity. It doesn't really generate any nitrous oxides or anything like you could have from a blast furnace. And also, I mean, carbon and coke could contain a lot of pollutants, other types of materials. But again, hydrogen, especially when we make it ourselves, is chemically clean as a gas. So we don't really add anything compared to the traditional blast furnace, rather vice versa.
It's clear that hydrogen, as you mentioned, as a clean commodity, offers great advantage in terms of emissions reduction. However, when considering the broader picture, I'm interested in understanding the overall environmental impact of fossil-free steel production. Specifically, when we assess the entire life cycle of the business, taking into account factors such as energy and resource requirements, as well as potential infrastructure changes. What are the environmental implications in this case? Could you please provide some insights into the holistic environmental perspective of the HYBRIT process?
That would be my thinking. The big bottleneck here is the availability of green electricity, like we talked about before. It's worth pointing out that we are going to use a lot more electricity in this process, both for the hydrogen production and also for driving the electric arc furnace, which uses electricity. In the traditional blast furnace, the carbon that we're using actually generates the energy as well. If you want to be really crude, the traditional blast furnace is really a huge carbon power plant with a bit of steel as a byproduct. It generates a lot of heat, for example. We're using that for district heating today. And if you calculate the amount of energy that you enter into this process in the form of carbon and coke, the traditional blast furnace actually uses more energy, slightly, than the hydrogen-based process are going to do in the future. It's just that energy comes in the form of carbon and coke and not in the form of electricity. So that's one thing. We're actually going to reduce our energy consumption in the future. We are, however, going to increase the electricity consumption. That is correct. And one bottleneck, like I said, is the availability of green electricity. On the other hand, this is a problem that needs to be solved in the world anyway. I mean, every industry that needs to decarbonize basically can only do two things. Either you use biofuels or you use clean electricity. Those are the two options that you have. Nevertheless, the Rocky Mountain Institute in the US made a study a couple of years ago on this process, and they arrived at the conclusion that if we could implement this hydrogen-based steelmaking technology globally today, it would be pretty much a zero-sum game considering the carbon footprint of the electrical system today. In Europe, it would, with today's electricity production, reduce the emissions by 30% or so. In the case of Sweden, it's close to 100 because we have green electricity. But if you look at Europe as a whole, and as a side remark, if you would do this in China today, you would increase the emissions by 30%, considering a lot of coal-based power plants and so on. But again, already today, globally, it would be a zero-sum game. So it has a lot of potential going forward.
Mm-hmm. Thank you for highlighting the crucial role of green electricity availability in the HYBRIT process. As you mentioned, the availability of clean and renewable energy source is a significant bottleneck that needs to be addressed in this process. Particularly in countries heavily reliant on fossil fuels or electricity generation, this is going to be a big issue. So this may raise a valid concern that while local technological advancement are important, solving the global issue of climate change requires a collective effort on a global scale. Many parts of the world are still far behind in adopting such technologies. With that in mind, do you think those other regions around the world can replicate this technology quickly and effectively later?
Definitely, and not only can, but need to. I mean, the steel industry stands for almost 9% of global CO2 emissions right now, and that needs to change. And that's actually something that we also identified rather early as SSAB. We have said very clearly that we want to make this technology available to the world also. Like you mentioned in the beginning, we're making this together with two partners, 𝗀𝗏𝗄𝗏, our iron ore supplier, and Vattenfall, our electricity producer. And by the way, I should mention that they have also committed to going fossil-free together with us. So in 2026, we will have also no diesel power machine in the iron ore mine, and there will be no fossil fuels used in the pelletizing process. And that's, of course, one prerequisite to have this really fossil-free value chain. We should remember that. And that is maybe something that is not available globally. Also, the mining industry needs to decarbonize in order to make this a totally fossil-free product. When we started this initiative in 2026, we actually created a specific company, HYBRIT Development Inc., that is owned by these three partners together. And that's where we do all the actual research, so that this one company holds all the intellectual property in order for us to make it easier to patent and also to license this technology to other parts of the world. We are creating a few patents because we would like to get the development costs covered, but otherwise we're very committed to making this technology available also to the world at large. We think this is important.
Great, thanks, Thomas. That looks really positive. It's truly exciting to see the potential for HYBRIT to be replicated in other parts of the world. Thomas, considering this positive outlook, I'm curious to know what you consider to be the primary challenge in scaling up fossil-free production on a global scale. Is there any unforeseen issue that you haven't anticipated?
No, not really. Like I said, the only bottleneck that I can see is availability of electricity, and of course the investment that needs to be made. At SSAB, we have made the strategic decision to let our blast furnaces become stranded assets, basically. We were going to close down our last blast furnace in 2030. And maybe that is slightly easier for us as a relatively small steel company. So, of course, you need a bit of investment, but with that exception, I don't really see any issues at all.
Really promising. Sorry, I forgot to ask about something during our discussion earlier on steel quality and properties. I'm really curious to know if the implementation of this technology will affect the recyclability or reusability of steel in the future. Will there be any changes or special considerations when it comes to recycling processes or the ability to reuse steel products?
No, none whatsoever. In fact, recycled steel or steel scrap is a scarce commodity in the world today. Obviously, if there was enough recycled steel available, all steel making should be based on recycled content. There is no doubt about that. But since the steel consumption in the world is increasing all the time, the recycled steel can never really catch up with demand, and we need to fill up the system with new steel from virgin materials. And by doing this with this hydrogen-based technology, we can then add more steel that can be recycled in the future without adding any CO2 emissions in the production. So we actually gain the advantage twice at least. And steel is basically recyclable forever. Recycled steel doesn't really have any aging. So this is actually a great contribution. We're actually going to increase the amount of steel that can be recycled, again, without adding any CO2 emissions to the world. So that's quite a positive thing.
That's really exciting to see the arrival of a structural material that's both CO2 free and infinitely recyclable. As a structural sustainability engineer, I can't wait to see fossil free steel being used in the buildings. So can you please give us some details on when we can expect it to be available commercially?
Well, like I said, we will start supplying this as a commercial product in 2026, but we cannot cover the world demand, obviously. In 2026, we will have a capacity of 1.3 million tons, roughly. We're going to increase that to at least 2.7 million tons by 2030, which means that we will cover approximately half of our Scandinavian steel production. And then we need to take it from there. And I think there is probably going to be a gap, let's say, between 2026 and 2035, where there will be a lack of fossil-free steels in the world. But I think at least in Europe by 2035 or so, you will not really see any conventional steel making anymore, because if nothing else, it's going to be cost prohibitive.
That doesn't seem to be a long time frame considering the size of the project. And also it's impressive that fossil-free steel will have limited commercial availability by 2026. That's really exciting. And let's move on to the last question. Last question is, do you anticipate any impact or disruptions that the adoption of fossil-free steel production technology will have on the steel industry, including fabricators, engineers, and distributors?
No, except the fact that they will be able to offer a product to their customers with much lower carbon footprint. Like I said earlier, our fossil-free steels will be chemically identical to the steels that we make today. You will not, unfortunately, be able to see the difference afterwards. So no disruption. If you talk disruption on a global scale, you could also ask yourself, is the world going to use radically different materials in the future than they are today? Are we going to stop using steel? And I don't think so. I mean, we talk a lot about the emissions from steel. And like I said, the global steel industry stands for somewhere between 7 and 9% of the global CO2 emissions. But that's just because we use a lot of steel in the world, because it is a good material and it is recyclable. If you look per produced ton, steel is actually a material with very low emissions. The only two materials that I know that have lower emissions are glass and cardboard, pretty much. But if you're looking at other metals, if you're looking at plastics, whatever, they have certainly much higher environmental issues than steel does.
Great. It's indeed a positive development for all stakeholders in the steel industry's value chain. Thomas, before we wrap up our conversation, I would like to ask, what message do you have for the steel industry regarding this technology that they should take away today?
Let's do it, and let's do it now, and let's show the world that we are a hard-to-abate sector that can be abated. And if we show together that this is the way to go for the future, that will also make it easier for other parts of the industry to follow in our footsteps.
Thank you so much for sharing your valuable insights with us today. We greatly appreciate your time. It's truly inspiring to hear about your HYBRIT project and its potentials. And thank you all for watching this interview, and I hope you enjoyed it.
So there you go. Thanks for joining our conversation with Thomas today. If you'd like to connect more with him, you'll find his details in the show notes. This is a truly exciting podcast which allows us to see what the future of steel looks like and what steelmakers are working on to pave the way for a greener future. We can only imagine what other technology is out there to revolutionize the steel industry. Food for thought till we see you next time. So hit subscribe, and if you liked what you heard today, please like, review or share with any metal minds you know. Let's spread the word. At HERA, we have a range of sustainability-related research projects, program guides and tools in play to assist our members who are embarking on a sustainability journey within their business. To find out more, you can find links in the show notes.